Okay, so this session is a hands-on session. The idea is to give everybody access to persistent memory and show you how to use the examples that we have for programming. I'm not in a hurry to start just in case a couple of other people show up, but I'm handing out these little slips of paper that we'll use to give you access to the machine. So everybody gets a number. I'll show you what to do with the paper in a minute. Okay, we might as well start. So this is actually, we call this a hackathon when we do these in the US, and we started doing them all over the world also. And the hackathons actually go for many hours. So we give people access to the machines, and then they hack on something, some program for a while. And in fact, like at Flash Memory Summit, I showed these slides, we gave people access, and then they continued to work on programs for days, because FMS was 4 days long. And then, so they have access, and you will too. The little slips of paper that I handed out, I'm going to leave the machine running for a few days. So even after this is over, you'll still have access. So, I think we have 2 new people. This is for you. This is a very important secret information. Don't tell anybody. I'll explain it in a minute. Okay. I feel like I'm one of those talk show hosts that runs around the audience. Okay, so everything that I talk about in this session is in this GitHub repo. So the only thing that you have to remember is today's date and the word PMDK Hackathon, Persistent Memory Hackathon. I tried to make it easy. So don't worry about taking notes. Every program example that I show you, every piece of code, every slide that I show you, it's all here in this repo. And this is a permanent repo for today's materials. So it's always going to be there. So you don't have to worry about getting access to the slides. Basically, I'm going to start with a couple of slides, but not very many. The whole idea here is to get you hands-on access. It's called a hands-on session, right? So we're going to do less talk, more hack. Okay. It works like this. You guys are sitting out there, and I've given each of you a username. So you might be PMM user 1, or PMM user 2, or PMM user 3, or PMM user 4. You each have a username, and in your browser, you go to this URL, devhost.pmmhackathon.io. And in a minute, I'll give you a password. Right now, you just have a username, but I'll give you the password in a minute. And that gives you access. That gives you access to our machine that has persistent memory on it. Okay, so this is a machine with Apache Pass, DC Optane persistent memory plugged in. And then each of you will have access to 8 examples of code that you can use as starting points. I did some in C, I did some in C++. I don't think I used any other languages in the examples just yet, but there's enough to start. And I will walk through the first 3 examples with you. But then you can walk through all of the examples and take as long as you want. You can ask questions and so on. All right? So when you log in, there will be a list of examples on the main page, and the first 3 that I'm going to walk through with you are marked as recommended examples, okay? And then we're going to go through quickly some background slides just to make sure everybody has the same background here. And I just want to point out, I'm giving you each access to this machine. Please don't try to break the machine by using up all the memory or something, because I currently don't prevent you from doing that. We're all just low security here. Okay, so if you've watched any of the sessions on persistent memory in this summit, you know that there's lots of ways to use persistent memory. You can use the storage APIs without modifying your program. You can use the libraries. You can use memory mode, which just looks like large system memory. Those are all too easy. There's nothing to learn about that. It's too easy, right? So you know about those transparent modes, but we're not going to worry about that here. Here, we're going to worry about what happens when you really want direct access. So remember this programming model picture that I showed in an earlier session. We're going to concentrate in this picture, I'm just going to keep going past this stuff, on this stuff on the right here. Okay? We're going to ignore everything else because it's just like I say, it's not interesting. This is the point of the hands-on. I'm going to give you direct access to the persistent memory. Now, every one of you, when you log into the system, the persistent memory will be at this path, /pmem. I've already created the DAX file system for you. I've already mounted it, so you can start using it right away. Okay? All right, here comes the exciting part. I'm going to kind of skip these things that we talked about in the earlier session, and we're going to get right to it. I just want to remind you, PMDK has a lot of different libraries, and the examples, we have examples that use different libraries to help you. So for example, one of our examples is a libpmobj example. One of our examples is a PMKV example, which for some reason I don't have on this slide. One of them is a memkind example, right? So the idea is you can try what you're interested in. All right? Okay, so now here's what you've been waiting for. So each of you has a username. Is there anybody who doesn't have a username? You came in later. Do you need one? Each of you has a username, and each of you knows the URL, and now you know the password. It's a highly secure password. Beijing-hack. There it is. You should be able to go log in. Thank you. Oops, sorry. And I'm going to do it too. So I'm switching from my slides to a web browser, and I'm typing in my username and my password. Beijing-hack. So if it worked, you should be at this page which says at the top, list of examples. Did that work for anybody? Does anybody see that page? Okay, I see some people say yes. So it worked for at least one person. Okay, and now here on this page are the 8 examples. They're called example A down through example H. Okay, and I'm going to walk through the first couple of examples with you to kind of show you the idea here. Okay, we're going to start with example A. So example A is about mapping persistent memory. It's just the simplest example I could come up with. How do I call in that? That's it. That's all it showed you, right? So if you click on example A, you go in to the example here, and you can see we start by explaining what mmap is. That, here's your application, and when you call mmap, you get a mapping directly to the persistent memory. So this is just a picture to help remind you what mmap is. And as I scroll down, I'm also reminding you what msync is. Msync is after you've made changes to the persistent memory, you have to call msync to make them persistent. Okay? Now, if you're curious about more information about mmap and msync, when you scroll down a little further, you'll see I put some links to man pages in here. The runtime environment, I just wanted to stop and point out, I've installed several terabytes of persistent memory in this system. And it's all mounted as /pmem. In fact, here's what happens if you type df. df is the Linux command that shows you information about a file system. And you can see, if I type df, I can see the device dev pmem0. This is half of the memory, or smaller, less than half of the memory. It's 275 gigs, and it's mounted as /pmem. And then, sure enough, I can also use the mount command to make sure that it's mounted with the DAX option. Okay, So you can run this if you want, but I've already kind of set this up for you. So this is just background information. And now I'm going to get to the programming example. That's the more interesting part. So as I scroll down in the example, I can see now I'm in step 2 here. This is where I've given you links to the man pages for the things we're going to talk about, like mmap and msync. Feel free to click on those links if you need access to the man pages. And here's the actual example. Okay? So the way that this hackathon works, the way that this tool works is, these are the files that make up this example. So example A is 2 files. It's this .c file here and a make file for building it. So here's the .c file, and you can kind of walk through it and see if you understand what I'm doing here. This is a very short C program, so you'll see right away when you get to line 23, this is where mmap is called. Okay? And the text that I kind of scrolled by, that explains what's going on here. I just wanted to draw you to it. So you can see how mmap works here. You can see down below where I'm calling stir copy, this one right here, to line 29, that I'm copying. I'm actually storing things to persistent memory. And this is an edit window, right? You can make whatever change you want here. So instead of saying hello persistent memory, I can say hello persistent memory in Beijing. Okay, you can just edit this. When you're ready to try it, click this green button below the program. See that green button? And you can see underneath the results of the build. So it built the program, and if there were any errors, like syntax errors, they would show up right here. And you have to go fix them. Okay? So this gives you access to the example. You can play with it all you want. You are in your own container. You're not messing up anybody else's copy of the program. This is your own tree. And then, as we go down here, to run the program, I've written you a little script. Here's what my script does. I create a file that's 1 megabyte in size on the persistent memory file system. I dump it to show you what's in it initially. It shouldn't have anything but a bunch of zeros. Then I run the C program we just wrote up above on that file, and then I dump it so we can see the result. Okay? So you can edit this script all you want. You can put whatever you want in here. If you want to put in a remove command and remove your home directory, you can do that. You can put whatever you want. So scroll down here, click the run, and sure enough, this just ran on the server, right? So you can see the commands are running. I echo them as they run. Here you can see initially we dump the contents of the file, and it's just nothing but zeros. Xdump just shows you a row of zeros to say that's all that's in the file. After we run the program, you can see it now has the string that you saw me type a minute ago. Hello, persistent memory in Beijing. Okay? So the program works, right? Now, like I said, this is the simplest program. It just shows you how to do an mmap and a stir copy. But it's a way to get started, right? It's the first concept is about mmap. And the examples get a lot more interesting after this. So this is the first one. So let me pause here for a second. Did anybody manage to get in here and play with example A already? You work on the PMDK team, so you don't know. Did anybody who doesn't work on PMDK get it working? Did any of you guys, have you got to the point of clicking the run button? Yeah, okay. Yeah? Okay, so now you kind of see the general idea behind this hands-on session. It's to put you in touch with code that you can edit and learn from and try different things. Okay? In case you're interested, at the very end of example A, I put a link down here. There's a little summary, and I put a link to the Windows version of this example. You can click on it in case you are not a Linux programmer and you're wondering, what does it look like to get to persistent memory in Windows? I put a link to a program here. But the server runs Linux, so you can't run this one. You could run it on your own Windows machine. It would run on any Windows machine. Because we use the standard interfaces, which work with files, whether they're persistent memory or not. And then anytime you want, you can click this little thing in the upper right here, and you can go back to the list of examples and switch to a different example. So that was an example A, and I think it'll be interesting for us to walk through example B together, because example B is actually a little more substantial. It does something more interesting. Example A just called it math. That was all it did. Example B is an example of the PMKV key value store. Yesterday, Shimon, who's sitting over here, gave a talk about this key value store, and I made an example for this hands-on session. So when you're ready, you can go into example B. And again, the text at the top kind of explains what the example is. And it's worth taking a moment to review this, because this is, trust me, this is the coolest part about our key value store. So I don't want you to miss it. A normal key value store looks like this. The keys and the values are on storage. And I mean a normal persistent key value store. Looks like this. The keys and the values are on storage. And when you want to look up a key and get a value back, you have to allocate a DRAM buffer, because that's how storage works. Right? Storage is buffer-based. The access is buffer-based. So in a traditional key value store, I look up a key, I get back a value, and it's a copy. It got copied into this buffer. Why is it a copy? Because I can't access it directly on storage. Storage is not byte addressable. But what if we had byte addressable persistence? Then you get this picture here, which is pretty cool. Now you can say, oh, I need to look up a key and get back a reference to the value right in its resting place on persistence. You can access it without copying it. So imagine this value is a 1 gigabyte audio recording or something. Right? I just saved us 1 gigabyte of bandwidth copying stuff into DRAM. Right? So this is the cool thing of a persistent memory resident key value store. You can access things right where they live. And I'm going to show you how that works. Now, as a quick review, what are the components that make up this library? I drew a little picture here to walk you through it. All of this should look kind of familiar if you were in any of the other persistent memory talks. Here's the persistent memory installed in our system. This is, like I say, a couple terabytes of DC Optane persistent memory. We're using, on this system, I use the ext4 file system in DAX mode, following the SNIA programming model, to expose persistent memory using MMAP, to expose it. I use libpmem out of PMDK to handle things like flushing and copying. Right? That's what libpmem does. I use it by calling libpmem-obj. Libpmem-obj provides allocation and transactions, and a bunch of other stuff, but those are the things we're using here. On top of libpmem-obj, we used it to write this library called the CMAP engine. The author is sitting right over here, in the second row there. Take a bow, Sergey. And so this is the concurrent persistent memory hash map that we're using to make a key value store. It's an awesome piece of software, by the way. It's very cool. And then we have this library called libpmem-kv that gives everything a uniform API, a uniform interface. And then here's the app that we're going to write, right here. Okay, so this just shows you how all these pieces work together. And it looks like a big stack. But remember, it's not a big stack. It really is about looking at the value. Once you look up a value, none of the software is in the path anymore, right? I'm just accessing the value directly. So I use this software to find the value, but then I have a reference directly to the information. So the stack looks big, but it actually is only big during the metadata operations. Okay, so I'm going to kind of scroll past my English description of this and show you the program. So here's the actual program. It's called PMDK. I decided this should be a C++ example, so it's a .cpp file. This stuff is pretty self-explanatory. It's include files and stuff. Just because it wasn't an interesting part of this example, I wrote the code that opens the file, and I put it in a separate file here. You're free to look at it, you're free to modify it, but it's something we can look at later if you want. I call it must open or create. We call that function, and it must either open an existing file or create it, and the must means it's going to automatically bail out of the program if it's an error. Okay, I'm going to scroll down. Here's a function I wrote for printing a key and a value. If you call this function and give it a key and a value, it just prints it to the output. Right? Pretty simple. You'll see how we use that function as a callback in a minute. All right, here's my main program. And the way the main program is designed to work is if you run it, PMDK, and give it the file, but no other arguments, it just prints out all the keys and values in the file. Just dumps everything to output so you can see what's in it. If you run it and just give it a one key, it looks up the value associated with that key and prints it. Or if you run it and give it a key and a value, then it adds that. So it's just kind of a little test program. I tried to make it as simple as possible so we can spend most of our time on the key value API and not on too fancy of a program. Okay, so I open up the file, the key value store, and if I was not given any arguments other than the file, then argc will be equal to 2, and here I am using the getAll API in the PMDK. So that gets a list of all the keys and values. And for each one, it calls this callback. And you saw up above I've written the callback. So pretty simple. Okay? Remember that callback is called with a reference to the value in its resting place on persistence. There's no copying of that value. What happens if somebody gave me a key to look up? Then argc will be equal to 3, and we use the get thing. So I'm going to call get, I'm going to pass in the key that I wanted to look up, and this is worth talking about. So this is a C++ syntax called a lambda function. In C++, you can create these unnamed functions anywhere you want, and they look like this. They have this funky thing with a square bracket and an ampersand here, and here's the argument. So I could have written another function at the top, but I wanted to show you this because this turns out to be really useful. This is how we end up doing a lot of these kinds of programs. We put the callback function right here, right where you're calling the get. So get will look up the key. It will lock it so that nobody can remove the value while you're messing with it. It'll call your function, your lambda function, and let you execute your code here. And then when you return, it can release the lock and return back from get. So this turns out to be a very popular way. You'll see this in PMDK all over the place. We use these, in C++, we use these lambdas all over the place. And you can see what it does is it just outputs a string telling you what it looked up. And then finally, if you give it a pair where you want to add something, you can see the API that we call is called put. Okay? So again, don't be afraid to modify this. In your browser, you have your own copy of this program. You can change it all you want. Won't hurt anything, and I encourage you to experiment. After I'm done making any modifications I want, I'm going to click to build, and it builds it on the server. You can see it's just running the makefile here, and it ended up building a program called PMDK. If you're a C++ programmer, this all makes sense. If you're not a C++ programmer, you probably get the idea of what we're doing. Hopefully. Okay, so how do I run it? Well, as I said, it can run in a few different modes. So I just wrote a little script. My little script is going to add the birth and death years of Bach and Mozart as keys and values. Right? That's a key, that's a value. Then I'm going to look up one of them. I'm going to add a few more, and then I'm going to dump them all. Just to do some simple key value operations. This is greatly improved from the previous version of this program, which did superheroes, and I mixed up universes, and all the guys in the audience said, "You can't do that." I had it terribly wrong. Okay, I'm going to run this, and let's just take a look at the output. So again, this ran on the server on real persistent memory. Here I am, you can see, adding these guys, and sure enough, when I look up this key, I get back the expected value that was stored earlier. not too surprising, since it is a key value store. Or if I make the call here to dump everything, you can see it just dumps everything out. This is my function that I called at the beginning called kdprint that prints everything. So the purpose of this exercise is to show you that, we've had sessions here on the PMDK and how it can do some fairly complicated things. We had the MemVerge guys give that session about tuning the PMDK and all the complicated stuff they did, right? We showed in some of our sessions libpmem, where you can just do flushing and copying, that can be pretty complex to do things. This is a key value store. It's a very high-level API. The APIs are get and put, essentially. So you can start using persistent memory in minutes with an API like this. It's very simple. And that's the point of example B. So I really do encourage you to play more with example B. It shows you how simple persistent memory can be. And I'm going to then walk through example C. Because again, my goal here is to give you some background so that then you can play with these examples yourself. Example C is for people who don't want to use a key value API. They want to build their own data structures. They want to do their own basic persistent memory transactions. I did this example in C++, because that turns out to be pretty popular for persistent memory programming. But we have other examples in C and other languages available. Okay, so in example C, I'm going to you build a little queue data structure. Sorry, this picture is a little small, but the idea is the queue has a head pointer and a tail pointer. And you add things to the head and you take them off from the tail. Boy, that is hard to read, but that's what it says. And, it's persistent memory. So normally, if I were to do this in normal DRAM, normal memory, I would just call malloc to these data structures, and I would have a pointer to the head and a pointer to the tail in my program. And if my program crashed, all those things go away. They're not persistent, right? But this is persistent memory, so I have to have a way to find this. Every time that I run the program, I have to find my data structure again. The way you do that with libpmem is this root object, right? You have to have a root object that tells you where's the root of my data structure. So you can see I put the head and tail pointer inside the root object in this picture. Now the code itself is down below. One thing I'm showing you here is just an excerpt here that shows you the transaction syntax. So we need a way to express, for the programmer to express, I want these operations to happen as a transaction. Right? Well, here's that same syntax in C++, the lambda syntax, right? We have a routine called run, that runs a transaction, and its second argument is a lambda. It's a function. And that means everything inside that lambda, right here, either runs or doesn't run in the face of failure. Right? So if we're in the middle of running this code right here, and the program crashes or the system loses power, when you come back, it'll either have completely completed or not even started. This is atomic. The lambda indicates the atomic code. That's another very popular way of programming with our libraries. Okay, so now let's actually look at the code. It's not very big, but it is a lot bigger than the previous example. There's a lot of, kind of standard stuff that you get out of the man pages at the top, which include files to use and stuff like that. I'm going to kind of scroll down to the most interesting part, which is the class that stands for the queue itself. And you may have seen this if you went to some of the earlier talks. The stuff that is resident in PMEM, the stuff that lives in persistent memory, you indicate it using the C++ templates. Right? So this P, which stands for persistent, says in this struct, this thing called value lives in persistent memory, and its type is a UINT6014. And in this struct, the field called next is a persistent pointer to this data type, which is in fact itself because it's a linked list. Once you've done that, we can now write the actual push function itself, which I showed you earlier. Nothing too surprising here, right? It's got the lambda, which says this stuff should be transactional. When you're doing a push operation, the first thing you do is you allocate a new node. That's what this does. This allocates a new node in persistent memory. Then you start filling it in with the value, the next pointer, you link it into the list. And again, this is all transactional. If somebody walks up to the server and yanks out the power cord in the middle of this, none of this happens, including the allocation. This memory goes back to the free memory list. Right? Remove is very similar. Again, we use this lambda syntax, say this is the transaction, and here's something kind of cool. If we discover something wrong, we can just call abort on the transaction, and it'll automatically back out anything that's been done already in the transaction. It automatically cleans it up. This is a check at the top, but imagine we had a more complex program where we did a whole bunch of stuff, including allocations and frees, and then we found some problem. We can call abort, and it unwinds it all for us and backs out all the changes for us. Turns out to make a program look a lot cleaner than without transactions. Okay, and then finally, there's a method in here to show what's at the top of the queue. I'm not going to go through the code in main, which you're free to, but it's pretty simple. You just give it an operation. You'll see it in a minute when we run it. Here I'm going to build the example. I'm going to scroll down. And so you can see there's, just like the key value store, this one has three ways you can call it. You can run the program, tell it where the persistent memory is, and give it the word push, and then the integer that you want to push onto our little queue of integers. You can run the program and give it the word pop, and it'll remove the thing from the queue. Or you can run the program and do show, and it'll show the contents of the queue. Those are the three operations. I wrote myself a little file here, a little script to do those things. You can see me pushing on 200, 400, and 600, and then showing what's on the queue, and popping a couple things off, then pushing on another value, and then doing the show. So let's run it and see if the output makes sense. So again, I echo the commands that I run with this little plus sign here. So I push on 200, 400, 600, and I do a show, and sure enough, the queue has this. Just in case it's not obvious, each one of these is a program running and exiting, right? This is the queue program running and then exiting. So we are kind of proving that our data structure is persistent, because otherwise it wouldn't have all three values, right? We ran the program 3 times, and then when we looked at the contents, it had the result. It is accumulating in persistent memory. Okay, then I pop off a 200, I pop off a 400, I added 800, and now only the 600 and the 800 remain. So it kind of proves that my queue program works. So once again, this is a simple C++ program. You can use it as a starting point for your own C++ program, and you're free to just edit it away right where it is. If you're like more of a Linux command line person and you don't want to use the web tool, I just want to point out I've made it so that on this upper left here, you can just get a shell window, and it will put you right in the same directory with your example. See, here I am in example C. There's the program that we just looked at. There's the script that we just ran for running it. So if you want to get in and just mess around with stuff, be my guest. I'm giving you all the access you need to do whatever you want. All right, going back to the examples. So those were the first 3 examples I wanted to show everybody to kind of get you started. Like I say, if you look at this list of examples, you'll find there's a number of them here to use as starting points. Let me point out one of the other kind of fun ones, which is example G. This is a use case that has been very popular these days, which is to use persistent memory as another tier of volatile memory, because you don't care that it's persistent in this use case, you just care that it's big and less expensive than DRAM. So this shows you how you can use the mem kind to put some things in DRAM and some things in persistent memory. Okay, so what I want to do now is pause, let you guys look at the code examples yourselves and see if any questions come up. And then in a few minutes I'll come up here and I'll take you through another example or answer any questions again. So I'm just going to pause and please take a look at the examples. And by the way, we have helpers in the room who are dying to help you with any programming problems you have. So my favorite example is actually example D. I don't know if any of you have gone through this yet, but in example D, I write a C program that has nothing to do with persistent memory. Then I take it and I multi-thread it to make it multi-threaded, safe. Then I take it and I convert it to persistent memory. And then I take it and I convert it to a C++ program on persistent memory. And that's actually in example D. So this can kind of show you, I get this question a lot. I already have a program and I just want to convert it. So what does it mean to do that conversion? Right? So I tried to make up a simple program where I could do that. And so if there's interest, I could walk through that example. I don't know if you guys are, should we do that? So I'm going to go into example D, and feel free to follow along in your own browsers if you want, or just work on something else if you're getting something else. But what I did was I thought I'd start with a very simple C program here, and I just tried to pick a problem that I thought I could explain in about a minute. Something simple. But what I decided to pick is a problem of counting the frequency of a word in a file. A word frequency count. Now, this is, I know these words are kind of small here, but doesn't really matter. My program creates a hash table. So this is just a picture of the hash table. You can see each bucket is a linked list. Okay? And so, for example, I pulled a book off the internet, War and Peace, and I ran it through this thing. And sure enough, the first two words that it found, oddly enough, were password and another word. I'm standing too close to it, I can't even read it. And this just that really is those words really do hash to the same bucket with my hashing algorithm. And so the whole idea is every time I see a word, I look in this hash table. Oh, witnesses is the other program. I look in this hash table, and if it's here, I bump the count up. And if it's not here, I add it to the hash table. And so that's just a quick picture of what a hash table looks like. But let me just show you the C program. It's really quite simple. I call it freq.c for frequency. And like I say, this is like a programming 101 program. I notice a lot of people who take programming these days don't get to learn C, but sorry. This is what I did when I was programming 101. I did it in C. And so here's the hash table. Every entry in the hash table is one of these things that has the word and the count and the pointer to the next entry. It's very basic C. And then the thing below is the buckets, the hash table itself, which I call capital H. You can see it's got a little, its name is capital H. That's the hash table. Here's my hashing function, which is not too interesting. But for every word that we find in the file, we call this function called count. So the first thing it does is it takes the word, it calculates the hash, and uses that to index into the hash table. So now EP, this pointer to an entry, that's the linked list that's in that hash bucket. Now we walk through and see if it's already in the hash table. If we find it in the hash table, we just bump the count up. We say, yep, I found this word again, and I'm counting the frequency. Otherwise, we have to allocate the new entry. Right? So very standard add to a hash table algorithm. You look at the hash table, if it's there, you use it. If it's not there, you have to allocate it. Right? So this is incredibly common, and That's essentially the entire freak program. It's got another function in there to print things. So if you build it and run the freak thing, you can see I actually have a little tiny file called words.txt that has some words in it. And then I can run this freak program on that file and then print out the result. So let's just run my little C program just to prove to you that it works. Remember, we're not doing anything yet that's using persistent memory with this program. So you can see, if I just look at what's in the this is kind of an interesting thing that happens with buffering sometimes. It's showing me these in the wrong order. But here's what's in the file. It's the phrase, "Now is the time for all good men to come together to your country." Then I ran the program, and it shows me the frequency count. And sure enough, 2 of these words happen twice, and all the other words happen once. So the program works. It counts the frequency of words in a file. So that was a very simple program, but it was single-threaded. And, most of the code that's out there that you will probably encounter for changing to use persistent memory is multi-threaded. Just about every program these days is multi-threaded because that's how people are learning to write code now. There are some exceptions, right? Like, for example, Redis, if you've ever played with that, they make a point of keeping Redis single-threaded, and then you run multiple instances of it. So you could actually argue that it's multi-threaded. It's just the way they achieve that is to run multiple processes. That's cheating. That's just the old stuffy way to do it. Yeah, go for the threads, man. Okay, so what did I do to make it multi-threaded? Let me look at my picture. So here's the same hash table, but I added these yellow boxes. These are locks. I added locks. I'm not one of these trendy programmers who does all this lock-free programming, at least not in this example. I'm just using these locks to protect each bucket. So whenever I'm going to change the contents of what's in a hash bucket, I grab this mutex. Or if I've found a word in here and I need to bump up the count, like I need to increase it, then I have a mutex in each node. I grab the mutex, I make changes, and drop the mutex. Okay? Pretty simple. You can see, though, there's 2 types of locks, and the tree has lots of locks. And I kind of did that on purpose to make the example more interesting. So now, if I kind of look at the resulting C code, it's really very similar to what we had before, only now, being the conscientious C programmer that I am, I add the lock to the struct where it belongs, and I add a comment that says what it protects, right? Remember, locks typically protect some data structure. It's good to think of them as protecting a data structure, not as protecting code. What this means is every time you want to change the count field, you have to grab this mutex. A pthread mutex T is just a POSIX data type. It's a standard, right? It's for a mutually exclusive lock. And then, like I said before, I also added a lock inside each bucket. It protects the entries field. So again, it's a pthread mutex T. The code is going to look very similar. We'll skip the hashing function again and go right to the count thing. So again, I take the word that I'm trying to count, I compute its hash, and then before I start looking at the hash table, I have to grab the lock for that bucket. So this is me doing the lock operation. Now I can walk through and see if I find it. If I find what I'm looking for in the table, I can now drop the bucket lock. I'm done with the bucket, and I just have the node to deal with. So I grab the node lock, remember it protects the count field, and then I drop the node lock. What if I don't find what I'm looking for? Well, then I'm going to add it to the bucket, so it's a good thing I already have the bucket lock. I allocate the new node right here. I add it with an initial count of 1, and then finally initialize the contents, and then finally drop the lock. So just a few lock statements, really, multi-threading this program. And now you can see, if I actually this multi-threaded version, it builds. Now if I go down, I'm going to call it like I did before, only instead of passing it 1 file, I'm going to pass it 3 files. And the part of the code I didn't go over is that it creates a thread for every file. So this will concurrently count the words in 3 files with 3 threads running at the same time. Now, I'm giving it the same file 3 times, but it doesn't matter, right? This could be any 3 files. Okay? So, here I am. I'm going to run it. And sure enough, you can see, whereas before the word is only happened once, now it happened 3 times. It was encountered in these 3 files, so it happened 3 times. And this shows you the multi-threading is working because, these guys are updating the same hash table concurrently, and it produced the correct results. In fact, I think you can just run it again, right? It should just keep accumulating. Let's try it. Run it again. I think it doesn't accumulate because I think I zeroed it out at the... Oh, I know why it doesn't accumulate. I'm not using persistent memory yet, right? In other words, my hash table at the end of this goes away. It's still just allocated in normal DRAM. So we have a multi-threaded program, but we haven't made anything persistent yet. It starts at the beginning every time I run it. It starts with counts that don't exist every time I run it. So now we want to make it persistent. So I have a simple, easy to understand, multi-threaded program, but it has a hash table, and I want to move that hash table to persistent memory. How do I make a persistent memory resident hash table? Well, here's my picture of my hash table. I still have blocks, right, where I set these yellow things. Only now I've converted them to the persistent memory safe locks. They're called PMEM mutexes. Right, that's part of PMDK. Alright, so that's one change I had to make. And remember, as I was saying before, how do you find this hash table? Every time the program runs, how do I find it? Right, it's a point. I need a pointer to it. I need to find the first data structure. So I do that by adding a root object, and the root object has this little pointer to the hash table that allows me to find it each time it runs. The root object, think of it as a well-known object that PMDK always allows you to find. Okay? And then the last change is that these arrows are now dashed. Okay, a little bit of a subtle change. See all these arrows here? These are pointers, right? This is a pointer to the first node in the linked list. Here's a pointer to the next node in the linked list. But why are they dashed now? What I'm trying to show you is that in PMDK you don't use normal pointers. You have to use object IDs. Because pointers have addresses in them that might not be the same every time you run them, right? The second time I run this program, mmap might return the persistent memory at a different address, right? In fact, it will. mmap intentionally changes the address that you get back every time you call, even if it's on the same file. It's something called address space layout randomization, ASR. I think I have it right. Address space layout randomization is done for security, so that a bad guy can't guess where some of your data structures are if he's trying to install on your data structures. That sounds really cool, but it's kind of a pain for persistent memory, right? Because then you have a pointer, and if that pointer has an address, like 40 hex in it or something like that, the next time you run, that pointer will be wrong because things got mapped at a different location. So PMDK solves that by making these pointers object IDs instead. They are location-independent pointers. You'll see what they look like in code. We call them object IDs or voids. I describe all this in this text. Read this, but don't read it right now. So here's my program. So once again, it looks very similar to the previous program. We have these macros that we use in C programming for persistent memory that tell the library these are the data types that I might have pointers to. It kind of registers these data types with the library. Okay, just kind of giving it a table of different types. You can see my root object has a pointer H to the hash table. So this is a pointer to a struct bucket. And we use this macro in C to say that this thing is an object ID because it lives in persistent memory. Okay, that's what the T-OID is. That's a type object ID. All right. The struct entry looks very similar to what it looked like in the previous example, except for, as I said, we changed the lock to be a PMEM mutex D because it lives in PMEM. And we changed these pointers to use this toid macro to to say that these things now need to be location-independent pointers. Now if we go down and look at our count function, again, it's going to look very similar to before. We calculate the hash, we grab the lock, we take this entries pointer and we walk through it. But remember, since these things are object IDs, you can't just dereference them directly, you have to use a macro. And that's what these macros do. This says, give me direct access to this object and make it read-write, because I might make a change. This one here says, give me direct access to this object and make it read-only, because I'm not going to make a change. It's really just a difference whether the macro uses the const keyword when it gives you the pointer back. So I'm walking through, if I find it in the hash table, I can drop the bucket lock, and here's the transaction. Right? This is a persistent memory transaction. I begin the transaction, I bump the count, and then I end the transaction. And you might remember in the Essentials talk, if you saw it, I mentioned it's so common that a transaction, begin and end, is the same place as where you grab a lock, that we made this macro also willing to grab the lock for you, and that's what it's doing. So we begin the transaction and grab the lock for multi-threaded safety at the same time. And then when we hit this TX end, that ends the transaction and drops the lock. Okay? Now remember, this is the C version of libpmobj. That's why there are all these macros here. In a minute, I'll show you the C++ version, which is much cleaner code. But they both do the same thing. Okay, so now, if it's not in the hash table, I have to allocate a new node. We have this thing called txzalloc, which means as part of a transaction, do an allocation and make it zeros initially. And the rest of it is just using the macros, as I said before, to add it, and it's all transactional there. So now, again, I'm going to build the version of the program that has now been converted for persistent memory. And I have a little script that's going to run it. Once again, it's going to create the pool. So nowhere in my program did I call the API for creating a pool. This is a choice. You can make your program create the file the first time, or you can have a system administrative step, and I chose to do that. I chose to create the pool, the file, where we're going to store the frequencies using the pmempool command. This is a command that we ship with PMDK, and it allows you to examine information in a PMDK file, but it also allows you to create it. So this says, create a pmobj file, give it this identifier internally as its layout. It's usually something that you've made up for your program. I called it freq for frequency. Give it a size of 10 megs, and here's the file name. Once I create it, you can see I start by printing out the whole hash table. Well, it should be empty the first time, right? There's nothing in it. Then we do some counts, and again, I'm counting these words files 3 times. Then print it out again. And count some more, and then print it out again. Well, so let's just run it and see all this in action. So I've taken that program, I've converted it to persistent memory. Here's the results of running it. Sure enough, I do create the file, because it's the first time I've run it. I call print, and there's nothing here, right? Then I count the words 3 times, just like before. I'm getting the same answers I got before. The script goes on to do it again. See, and now you can see all the values doubled because I'm counting them again and they're just accumulated. Right? In fact, in this script here, I can just run it again. I'm just going to do something quick. Run it again. Sure enough, now the first time they're all 6s, and the second time they're all 12s. Right? It's just going to get bigger every time because it's just sitting in persistent memory. Every time I run this, it's just going to add those counts. Keep running it, right? These numbers get bigger every time because this hash table is sitting in persistent memory. So we reconnect to the persistent memory and we're adding the counts to that data structure. So I've proven that it's persistent, right? Okay, so that was the simple C program that has nothing to do with persistent memory, converted to multi-threaded, converted to a C program that uses persistent memory. What would it look like if I did this exact same example in C++? So to do that, I made it, this is example D. I made it the next example, example E. It's the very same problem, only now I call it Freak PMM CPP. It's the CPP version of the program. So again, like I showed you in the CPP example earlier, there are some standard headers that you have to include. It's easiest just to start from an example. You can see now in my struct entry, I use those C++ templates to mark where the pointers are, and I use the template P just to say that something lives in persistent memory. So I don't have all those ugly macros. This is real C++ syntax, right? I'm just using the templates. And then if we go down to the count function, where we were doing the count just like before, it's going to look very similar. First, I calculate the hash, I go to that bucket, I grab a lock, search if it's already in there, I drop the bucket lock, I lock the entry, and I run a transaction that bumps the count. Remember in C++, the way we do these transactions is with these lambdas. Right? So it's actually much cleaner. It's all no macros, no made-up syntax. This is the real syntax of C++. If I don't find what I'm looking for in the buckets, then I have to run this transaction instead. It allocates a new entry in the table. That's this part, and fills it in, adds it to the queue. So that's the cool part about using the PMDK from C++. It actually looks very much just like normal C++. The only kind of weird things that happen were those little templates that I had to put around the fields and this transaction syntax, right? This lambda syntax. So if I run it, well, I'm going to build it. Build. I'm going to essentially do the exact same running program. Running script, I'll click run, and sure enough, it counts the words in the file and prints them out. And then if I run it again, those should accumulate. And sure enough, they went from 3 up to 6. And if I just keep running it, each time I run it, it'll just keep accumulating, right? Sure enough, it does. You can see them getting bigger because they're sorted persistently. So that's the same example, but done in C++. So, this is just a little hands-on session where you're looking at examples, but all these things are in the repo, right? That I pointed to, PMM, Hackathon, repo with today's date. So if after you're done here, and 2 months go by before you need to do some persistent memory programming, remember this example, right? Because this walks you through absolutely everything that you did to get from a new C program or C++, either one, to something that runs in persistent memory. So that's the point of this example. All right. So I'm going to let you continue to hack away at your examples. I just thought that we'd walk through that one because it's my favorite one. Like I said, my another favorite one is using this volatile memory. And if you're looking for something that's advanced, look at example H. This is a program that has 3 bugs in it. And we show you how to use our PMM check tool to find the bugs. And see if you can find them using the tool. It's a bit of a challenge. But we give you the answers at the end, so it's not that. All right, I'm going to let you hack.
It wasn't until I actually did the patch update for PSDO and TVB that I started looking. Unit 9. Are you good at using TVB and stuff here, right?
Yep, the PMM TV example did.
What's the version you've got?
Of which? Of the
TVB.
Well, it doesn't use TVB. It uses the engine that was based on TVB code.
Okay.
But I don't actually use the TVB library, so that must be the difference.
Yeah, because I'm actually using PSTL
I see.
concurrency.
No, Sergey, I forget the lead, but he took the concurrent out of TVB, converted it to persistent memory, and then added it to our tree. So it's not in TVB. It's in our. So I guess the good news is that the other stuff works fine with GCC now. So I must be fairly up to date.
Yeah.
Yeah, so I'm up to the 5.2 kernel on FC30, so, you know. Yeah, that is interesting though.
9211? Yeah.
Yeah.
No, sorry,
No, 5.2.
No, I'm on. I got GCC 921. 0827.
Oh, you are ahead of me. So I haven't done a DNF upgrade on this.
Yeah. Then I was like, should I try and recode? I tried to then recompile or create a separate version of GCC 8.
Yeah.
So I could keep my, because I didn't know what the issue was.
Yeah.
And then run into all sorts of libc issues and stuff, going backwards versions, and it's like, after I get out in GCC 9, I have to get there anyway sometime. But yeah, once I...
what a headache.
PSTL's header only, so as soon as I get on the repository, I checked out 0522 or something, and I was happy again.
Wow. I'll be on the lookout for that.
So has anybody gone through any of the other examples? Found anything interesting? I'm going to leave the machine up. You can use the credentials that I handed you over for, I don't know, the next 3 or 4 days. So it'll be up. You can use it. I'm going to stick around here until the end of the session. If you have any questions, I'm going to go ahead and turn off the screen stuff. But thanks for coming to the hands-on.